In the previous sessions, we have discussed how to design a analog IIR filter, right? Now in this session, now the next session will be on design of digital IIR filter. Now, what is the difference between digital filter and analog filter? Why analog filter and why digital filter? Can anyone? What is the difference between analog filter and digital filter? What do you think, or why we need to go for digital IIR filter? Is it not sufficient if I design only analog IIR filter? Is that not okay for the DSP processor? Why digital IIR filter is required? No, no, leave it IIR, FIR. Digital filter normally. So in the previous unit, you got to know that why filter is required, right? And we accordingly we try to design the filters for a given specifications. Then, if I want to convert that designed low pass filter, if I want to convert it to high pass filter, and that's where we learnt it from the transformation of frequency topic. Similarly, the design of analog filter, now once we have done with analog filter design, again what is the necessary of digital IIR filter design? Already we have designed and filters, right? Okay, can anyone? You might have experienced in your labs by designing a amplifier, like most of you the times the two group students will be doing the experiments, but one of the table getting the output, the other's table will not getting is will be not getting the output. This is a common thing that most of the analog lab we the many students will be facing. Though the circuit is same, the values are same, the resistance is same, everything most of the times remains same. But still, sometimes one of the batch will be getting the output for the same circuit, but other students will not be getting the output for the same circuit. That is not that was the same thing was not true with respect to digital lab, right? I think even if you have also observed these kind of problems in your regular labs. Now that's where, like, why digitalization is required. No two analog system with the same design will give me the same response. That's one of the very important point here, because analog components are temperature dependent. It depends, and even some of the conditions of your hardware, like transistor, like diode, like the capacitors, mainly the memory elements, to be more precisely talking about the capacitors and inductance, will be the values, or the specifications will be going to vary from one manufacturer to another manufacturer, and along with that the aging of components. Certainly, analog components, as the ages as his age increases, definitely we will see the degrading in the performance. The quite a good example is your mobile phones. At the very new my mobile phone, the charger or the battery will be very fantastic, and so that it will be giving me that 48 hours of battery backup. But the same case is not true as the days to go, or as the days passes. Certainly, my the performance of the battery decreases may from 48 hours to the 24 hours or sometimes even half day, right? So that's how the circuit responses with the component aging, right? So this is one, these are the major challenges that we what we face with analog components. So with this, that's one of the solution, okay, the very another very important change in the specifications every time. Change in the specifications require change in the hardware, entire hardware I need to change. Sometimes what happens, if I ask you to design for some frequency analog amplifier, and if I ask you to change the frequency from f1 to f2, then once again you perform a mathematical calculations and you need to design the values once again. And the how the values changes, you need to change the resistance and capacitors for that, or lc value you need to change, right? So l and c values got changes, again you need to remove those two components from your the circuit board, and once again you need to replace the fresh values of the L and C values. So this is, I'm speaking about only a lab oriented experiment, guys. And this is not true with some the devices like speakers. If I want to design, right, if I want to design a speakers for different amplifications, then I every time I cannot change my speakers. Yeah, is it not? So that's where uh, it is not that reliable and the user friendly aspects when I want to change any specifications in analog domain. So what we do is, it's always better and easy for me to go and change in the digital domain. And most of the times when I say that digital domain, it's always I will be playing with flip flops and registers and processors. So what happens is, there is always an option for me to change the values in terms of programming, and I can change my value of content of register by programming, and hence in turn I can able to see the change in the specification gives me the change in the values give me the change in the specification, obviously without hurdling my system's requirement. So that's how the importance of digitalization lies. Okay, so these if I go on telling, there are many n number of points where digital systems are much better when compared to analog circuits. Okay, so that's where easy to reproduce in large number of quantities, and when you have the independent specifications, so it is very quite easy. And anything that you want to make understand for your processors, yes, obviously it should be through logic 1 and logic 0, and for which, if you have a strong hold of digital circuits, or if you have a more number of digital designs, then it could be very easier for us to handle digital circuits rather than the analog circuits. But at the output side and at the input side, the real time processing must be done through the analog. But what we do is, we simply catch the input signal, and later point of time we convert all the analog components into digital components. We convert it to digital circuits, or we convert that analogous input to digital input by using analog to digital converter. Similarly, at the end, we once again go for taking digital to analog converter help, where all the sampled or the computed digital values in turn converts into analogous output. So now about this particular chapter, it's all about design of filters. Once again, it is digital filter. Now, one thumb rule you have to understand here. I say thumb rule because this is the fundamental concept. Okay, guys, listen carefully. This is one of the very important point. Now, when I say that analog filter, am I there in the connection?
Yes, sir.
Okay. Uh, Analog filter. So, what is the representation, mathematical representation of this analog filter? Can anyone? What is the representation of analog filter? How do you represent mathematically? What is the mathematical representation of a analog filter? You wrote a here on this already. You got to know how a filter is going to be represented. Another, what we call it? How do you represent? Guys, come on. This is too bad. Hmm? Frequency response. Okay, like what I'm trying to say is what type of variable. You again use Madhuri for in terms of mathematical transfer function. What type of transfer function? Complex exponential signal transfer function, frequency response, correct. But yeah, you represent projecta. Very good. We try to represent the analog filter in the form of transfer function, right? Very simple. So this is my transfer function. The transfer function will be having a kind of let me assume that if it is a all pole system, so where ak is the some gain of the filter, then followed by s minus a, right? So this is somewhere else we try to represent our the analog filter, where which consisting of normally numerator to the denominator, where denominator is this speaks about poles or the order of my filter. Now, very simple. This is mathematically what is this transform? What transform it is? It is Laplace transform, right? It is Laplace transform LT. Now, when I say that I want to move from analog to digital filter, so I am trying to move from analog to digital filter. Once again, to represent the filter, what is to be done? I'll come back to the chat window. Now, come on, tell me why, how do you represent the filter? That's good. Like Z transform or Z transform that we try to make use here. Which means now I need to represent my digital filter with respect to transfer function. Then again, this will be having some numerator and denominator. How the point is very simple. You already designed the H of S. Now the what you need to learn is how do you convert? How do you convert the analog filter HS into HZ? So if you able to understand what is the procedure to be followed to convert from HS to HZ, that is nothing but design of an IIR filter. For any filter that you want to design, maybe it is digital, yes, of course, uh, or all the time, like anytime you want to design the digital filter, first and foremost thing is you must design an analog filter first. You need to design HS. How do you design HS? So HS is going to be designed by deciding how many poles are required to my system. So now how do you identify the poles? Now poles are identified by two mains. So one is Butterworth and another one is Chebyshev. By considering these values, I calculate the value of n. So followed by I calculate omega c. So in turn, so I will be able to obtain my HS. So that is nothing but my analog filter, right? So once I design the analog filter, the rest is convert this HS to HZ. That's it. Now the point is how actually I need to convert that into HZ. So that is one of the very important point here. So you need that point to be highlighted here. Now what we do is, the point is very simple, guys. There are different ways. The one simple technique I'll tell you here: anytime you go from HS, anytime you go from HS, so this HS is nothing but a Laplace transform. Laplace transform is nothing but a definition with respect to integration, is it not? So I can represent integration in another way, that is reverse operation of integration is nothing but a differentiation, d by dt. So another one is, the another way we represent this equation in other way is difference equation. Difference equation. See, in analog form, the mathematical equations, any mathematical equations you take, right, right from the Laplace transform. So it is represented in the form of integration, or the reverse operation of integration we call it as a differentiation, or even difference equations. Okay, difference equations, sometimes we call it as a sampled versions of a d by dt. Okay, for the time being I neglect this, leave it. But any signal you take in analogous form, it will be in the form of integration or differentiation. Now we try to take this integration to digital aspect. That is where, how do you make a integration, or by programming language, in that way you need to think. I may be taking you little in-depth analysis. Try to understand this. Later on I'll make the job very simple, kind of thing. But try to I'll just wanted to take, like if you under, it is not only in the perspective of DSP I'm speaking, it is in the perspective of any mathematical equations, how you take that mathematical equation into programming model. That's that the intelligence of engineers lies in connecting all these mathematics to a programming model. That's where the real engineers take a very successful thing. Now, you given a quadratic equation, given any algebraic equations, you are familiar with writing those kinds of the mathematical equations onto the programming. But the point is, if there is a integration model or d by dt model differentiation, and how do you take up this? Because my Laplace definition is in terms of integration, right? So that's where I have a numerical integration model. So there is a integration, I need to convert it into numerical values. If and only if I get these value in numerical values, integration values in terms of numericals. Numerical means any numbers in the form of integer or floating point values, then it is very easy for me to put it on in the form of programming. Now tell me, which technique is present to convert this integration model into the numerical model in mathematics? Which is that any idea? You have learnt this. Any idea, guys? Any idea or not? No idea. See, have you heard about, now you tell me yes or no. Just now, have you heard about Simpson's one third rule or 3 by 8 rule? numerical integrations. Simpson's one-third rule or 3 by 8th rule, Newton forward difference method, backward difference method, Bailey, all these terminologies I'm taking from your fourth semester or probably in the third semester mathematics. M3, M4. Yes or no? Tell me at least. You just type Y or N at least if you are bored of typing that values. Have you not heard about the Simpson's one-third rule? Simpson's one-third rule or 3 by 8th rule. See, this is the technique. If you, I still recommend the all the students. This is one time where this is one platform. If you want to explore it. It's left to you again. To understand the importance of the mathematics and the physics concept. So there is one textbook by Grival, engineering applications, engineering mathematics by Grival, one of the very fantastic textbook to understand the application part of these integration and differentiation in terms of both electronics as well as mechanical engineering perspective. So only then, once you understand those the fundamentals, only then I can able to apply it to my engineering aspects. Okay, so try to go through that textbook. He has explained all the points very fantastic way and with a good number of examples. And to be frank, to be clear, if you want to attempt the exams like GATE or any other the IES, Indian Engineering Service kind of exams, if you want to apply, then definitely there a 40% weightage of the question paper in the GATE exam. Around 10-20% weightage will be given on mathematics itself, and followed by even after your successful clearing the gate exam, once again you are supposed to give the interviews in any IITs or ISCs. Then there also they will test your mathematics skills, mathematical skills, not by giving the equation and solving it, how to apply, how, where to apply, when to apply the transforms, and then the importance of your the algebra, like the two variables, solving the variables using the matrix method. All these are plays going to play a very important role. So that's where, guys, try to understand these things very carefully. Now see, by using Simpson's one-third rule, or in terms I say that numerical integration generally, so it is numerical integration. I make use of this numerical integration. I can by considering these algorithms, and I convert that into the numerical forms, then finally I can able to put it in the form of programming. So this is how we try to convert the integration and differentiation into numerical values. Okay, so now why I'm trying to talk about these kinds of integration and differentiation is, see, any filter, if I want to design or if I want to move from this, what is to be done? How do you, how, what is the definition of h of z or x of z? So h of z or x of z will be having, so input in terms of x of n, right? Summation, some minus infinity or 0 to infinity. It is how it is going to be defined, right? Some with some constant or coefficient value. Here, if I want to hz, if I want to calculate hz, so what will be the input for my z transform definition? Definitely it has to be h of n, right? If I have a h of n value, then it is very easy for me to calculate z transform. So how do you obtain z? How do you obtain h of n, which is a discrete form of your input? How do you obtain this h of n? So if I take inverse Laplace transform, hs I already have. If I take, let me write it here. Already I have hs. If I take inverse Laplace transform, what do I get? I get ht. Am I right? So what is this? It is nothing but a continuous function, right? Now I need hn. What is to be done? I have continuous function. I simply go for sampling with some n samples, which means that the obtained ht is going to be sampled at some sampling frequency t. So therefore, after some sampling frequency, what do I get? I get hn. That's it. Now, once I got to know about Hn, so this is very easy. Just simply apply the Z transform, you get Hz. So this is how we move from the Laplace domain to Z domain. It is nothing but moving from analog domain to digital domain. So this is the technique that what we are trying to use. This is the technique what we are trying to use here. So the first technique is, okay, I'm sorry. Okay. The first design is the filter designed by impulse invariance method, and the second method is I have a integration, because the Laplace transform definition is is going to be modeled with the help of integration. Now it is nothing but I make use of this integration, and if I go for reverse process, that is where it is nothing but a differentiation. Now now we make this differentiation or differential equation in turn. So I have a differential equations. I make use of the approximation of derivatives, where I'll be using that the numerical integration method to calculate the h of t. So it is all about calculating h of t, guys. That's it. Impulse invariance method is nothing but, as right now I told you, h of s I will be having. I take inverse Laplace transform. I'm going to get ht. I sample this. In turn, I will going to get hn. Then I apply zt. Then this is going to be my h of z. Very simple and straightforward. So this is digital filter designed by impulse invariance method, digital filter designed by approximation of derivatives, and the third method is digital filter designed by bilinear transformation. The basic fundamental is analog design. Any specification given, you first design the analog IIR filter. Once you done with this, okay, then go for transformation from Laplace transform to Z transform. That's it. In order to move from this domain to this domain, I have three different methods. One is impulse invariance technique, bilinear transformation, then the other one is the approximation of derivatives. So these are the three methods that is going to be discussed in the entire chapter. I have a derivation for this and all the three. Then for each of the method we'll try to discuss 2 to 3 examples, so so that it will make you comfortable in that. So probably I need another 4 5 days of time to complete this entire chapter. Probably okay. Let me take 2 days per concept. So I'll take 6 days. So that is going to end of the chapter or unit. We'll be left with after that we'll going to live left with only one unit. So that's once again very easy. Then that's IIR to FIR conversion. Okay. So with this, let me stop this class here itself.